Bismillahirrahmanirrahim. This video is about sampling theorem from chapter number 7 of Signals and Systems book by Mr. Oppenheim. And this is on the request of a student. So let's see. First of all, just to give you an idea, if there are, let's say, three signals here, you can see x1, x2, x3, and there could be point where the values are same. And if we happen to have taken the data from here, then we don't know where this data or this amplitude is for which signal. And same here, same here. Therefore, just by using the amplitude value, we cannot represent the signal. We cannot recreate the signal. So with that, we need to have the bandwidth of the signal also. So if we have the bandwidth, let's say it is 3 kilohertz, and if we take samples sufficiently close together, we'll see that it has to be greater than twice of that. So that means greater than 6 kilohertz sampling. Then we can reconstruct this signal perfectly. Okay, now we'll be talking about what is known as impulse train sampling. This is our signal xt. Here you can see it is being multiplied by a PT signal. PT is the impulse train. The signal is the impulse train, impulses spaced at equal distance. And the multiplication will result in this signal, which we'll call XPT. So XPT is XT multiplied by PT. A couple of points here. The impulse train PT is referred to as the sampling function. So this is referred to as sampling function. And then the period is the sampling period T. And the fundamental frequency we know is 1 over 2 pi f, and f is 1 over t. So omega s is the 2 pi over t is known as the sampling frequency. Now this pulse train can be described as a summation with the summation function. Pt is summation minus infinity to infinity and delta t, but this is shifted. You can see this delta is shifted here, then shifted here, same way. Therefore, this shifting is represented by minus nt. So this is the representation of the impulse train. Now, if we take a very simple example that this is the signal and we have just one impulse at t is equal to 0, then what will be the sample? Just this point here. And this will be like shown here. This will be represented by, or we'll call it xt0. So let's see from here, a unit impulse multiplying xt by a unit impulse will get xt delta t minus t0. And in our case, it will result in the output as xpt0, xt0 delta t0. So this is for the simple impulse. The only change we are getting here is the x will now be taken, the value of x at t is equal to 0. So value of t at equal to 0. Now we'll generalize this idea. We had this pulse train equation, and we had seen this, that xpt for single impulse was this t0x is at t0. Now for multiple impulses, the xpt will be summation x nt. Instead of t0, it will now be nt because there are many impulses, and delta t minus, in case of a t0 again, there will be nt because there are many impulses spaced as, let's say, 1t, 2t, 3t. So this is our equation 7.3 representing the total result or the output. Now, point to remember that if we take convolution in time domain, remember the sign is for convolution. So convolution of two signal in time domain means multiplication of the two signals in frequency domain. But multiplication of the signals in time domain will result in convolution in frequency domain along with a multiplying factor of 1 over 2 pi. So this we have to remember. And now coming back to our signal, this was the output signal we had. And this is in time domain. And from the article 4.5, which is known as the multiplication property or the modulation property, you can also call it amplitude modulation property. What he's saying that if a signal named RT is ST plus PT in time domain, then in frequency domain, RT will become RJ omega, and these two multiplication will be now the convolution along with 1 over 2 pi. Now in our case, we don't have RT, we have XPT. So let's see what will happen to that. Remember this 1 over 2 pi coming from here. So in our case, XPT is XTPT in time domain. Therefore, in frequency domain, it will be XPJ omega 1 over 2 pi. Here it will be XJ omega and convolution PJ omega. So this I'm calling 7.4. Actually, in the book, he has used the integral form of the convolution, and he is calling it as 7.4. But I prefer this because this is simpler to use, and Math GPT has used this. So thanks to them. So we were here, and now let's define the from example 4.8. The Fourier transform of a periodic impulse. So this was the impulse in example 4.8, and this is in time domain. The same impulse in frequency domain will have this shape, slightly scattered, and the magnitude has also changed. And this can be now written in the frequency domain as xj omega 2 pi over t summation of delta omega minus 2 pi kt for the train in time domain to train in frequency domain. Now this was xt. In our case, our train is pt. This is the train pt. So in frequency domain, it will be just like this, only for xj we'll write pj, then 2 pi t, and delta, same thing. And if you want to transform it in terms of omega s, we know that omega s or the sampling frequency is 2 pi over t. So 2 pi over t can be written as omega s. And therefore, this will become k omega s. So this is our equation 7.5. Now we have two equations, 7.4 and 7.5. We'll plug in 7.5 into 7.4. So substituting 7.5 in 7.4, just follow this 1 over 2 pi xj omega, and then this is from here pj omega, equivalent to pj omega. And now we'll use a linearity property of convolution, that a constant a convolution of the summation means that we can take the summation over a whole of the things a convolution b. Same here, this we can write inside the equal sign, just like here. So we have taken the constants out. We bring xj omega inside the summation sign. This 2 pi gets cancelled. It is 1 over 2. Rest this remains same. The convolution of a signal with a shifted impulse simply shift this signal. So like this signal, convolution with a shifted impulse can be written as the signal with the shifted value of t. This value. So this is explained in equation 2.70. So we'll follow the same thing here. This is the signal. This is the shifted impulse. So that means we can write this to be xj and this value here, k omega minus k omega s. So this is our final equation. That is xpj is a periodic function of omega consisting of a superposition of shifted replicas of xj omega. So basically these are the shifted replicas. So one for 1k, then 2k, for 3k, this will be changing. And they are all scaled by 1 over t. And this is illustrated in the next figure. So this is our frequency domain spectrum of the input signal. This is frequency domain spectrum of the train, impulse train. So what will happen is that this spectrum will now ride on this train using this formula. So it will be like this. So 1 over t is the magnitude, and this is now repeating at 1, then at second, then third, like this. So this is our representation of xpj omega. And the important point to note here that this diagram, omega s has to be greater than 2 omega m. Now this is omega s. It has to be greater than 2 omega m. I'll explain it in the next slide. That is, xpj is a periodic function of omega consisting of superposition of shifted replicas of xj omega scaled by 1t as shown in figure. So just last slide also we discussed this, but now you can see it with the diagram that these are the replicas of the original signal. Now, just a point to note, the omega m is the maximum frequency or the band of the input signal, and omega s is the frequency of the sampling function, omega s. Now, let's see here, I will explain what does omega s greater than 2 omega m means. From here to here is omega m. Similarly, from here to here is also omega m. So the sum of the two plus this one is equal to omega s. That means we can say that omega s is greater than 2m. Omega s is greater than 1m plus 1m 2m. And the signal is easily reproduced. There could be a possibility where omega s is less than 2 omega m. That means this is omega m, this is also omega m. So 1 omega m, 2 omega m, the sum of the two. Now omega s is less than the sum of the two. Omega s is less than 2 omega m. And in that case, you can see the signal has now distorted. It is not as clear as this. And this effect is called aliasing. So we'll be discussing as we keep going further. Okay, now the sampling theorem in short is just explaining the same thing, that x be a band limited signal, xj omega, where the frequency is greater than omega m. That means this is omega, and if the frequency is greater than omega m, then xj omega has to be 0. Now you can see the xj omega is up to this point. Any frequency greater than omega m, xj is 0. So that is what he is trying to say here. Now xt is uniquely determined by the samples if omega s is greater than 2 omega. So we just discussed that if it is greater, then we have a gap here and this can be easily recovered. So we'll see next. Given the sample, we can reconstruct by generating a periodic impulse train, just like here, with successive impulses having the amplitude that are successive sample values. So these are the sample values, this amplitude. And the important point is that if we pass this to an ideal low pass filter, so now this is low pass filter. If we pass through a low pass filter with a gain of T, the cutoff frequency greater than omega m and less than this frequency. Now this is important. The cutoff frequency omega c is the frequency of the filter. It has to be greater than omega m, but it has to be less than this point. Now this point is from the next signal, this point is omega s minus omega m. If it goes here, then it will get into the domain of the other pulse. And if it comes further closer, it will chop the original pulse. So this is important, that the omega s has to be greater than omega m, but has to be less than omega s minus omega m. And the resulting output signal will be exactly xt. So if we use this filter, we can easily recover the signal, time domain signal. And the diagram for this whole thing, we have seen this. The multiplication part was xt, then we had pt, will give xpt, and then we are connecting a low pass filter to get the xt. And just a point that we have mentioned this condition that omega s has to be greater than 2 omega m. This 2 omega m is called the Nyquist rate. And the Mr. Harry Nyquist actually discovered this and in his theorem, and that is why it is called Nyquist rate. So Nyquist rate is 2 times the maximum frequency of the signal. I hope you have been able to follow this. Please let me know through your comments. Thank you.